Okay, welcome back everyone. Today we're going to look at balanced and unbalanced forces, and essentially we're going to be looking at force net equations. So we recently examined that force net is equal to mass times the acceleration, but a net force is the sum of all of the forces. So in order to help us create force net equations, we have to start looking at all of the different forces that come into play. And in order to look at all of the different forces that come into play, we have to create what are called free body diagrams. And so in these diagrams, there's three pieces of information that are crucial. There's the type of forces that are acting on the object, there's the direction of the forces, and then there's the magnitude of the forces. So that's the number that goes with the vector arrow. And it's important to create force net equations in both the horizontal and the vertical direction, so your x component and your y components. If the net force that's acted on an object is 0, then that means that there's a balanced force. That means that the pushing force is equal to the pulling force. And if there is a balance of forces, we've looked at it in the past that Newton's first law is that an object will stay in motion until an unbalanced force acts upon it, either speeding it up or slowing it down. But if it's at a constant velocity or it's at rest and it's not moving, then there is an equal balance of forces. If the net force acting on an object is not equal to 0, then there's an unbalanced force and it's either accelerating or decelerating. We look at four specific types of forces. We look at the force of gravity. We've already looked at gravity, and we know that gravity always works towards the center of an object. And so in our diagrams, the force of gravity always works straight down on the object, whether the object is on a flat surface or on a vertical surface or on an angled surface, it always works straight down towards the bottom. The force normal is always perpendicular to the surface. The force applied is the force that's exerted by machine, human, or animal, and the force of friction is its opposing force of motion. So we will just start with diagrams. If we look at a child crawling east along a carpet with a constant speed, so now we're starting to look at some key words. Constant speed means that there is no unbalanced forces. Okay, so the direction of motion is east. We say direction of motion. And this is how we Bob Ross a child crawling on the floor. Okay, so when we looked at Newton's third law, we had said for each force there's an opposing, equal, and opposite force. And so we are going to look at the first two here, force of gravity. Remember, from the center of the mass, it's always going to work straight down. This is force of gravity. And this opposing force then would be force normal. Now notice I wrote a capital N. This is not force net. Force net is written as NET. Now you'll hear me quite often say, is this child levitating or is this child sinking through the floor? And the answer is always no, which means that the forces are balanced. The force normal is equal to the force of gravity. The child is moving east, and so the child is applying a force in the easterly direction against the floor, whereas the floor is applying a force of friction, an opposing force. So force normal, force gravity are a pair, and force applied and force of friction are a pair. Okay? So what do we see happening in the x direction? In the x direction, we see that force net is equal to the force applied. I'm just going to leave it as FA. You'll see it quite often written as FAPP, but I'm just going to write FA. And its opposing force, remember force net is the sum of all forces. Keep this in mind. So F net is going to be equal to force applied plus, that's the sum. And what's its opposing force? Well, the force of friction. The force of friction is working in the opposite direction. And opposite is indicated by negative FF. In the y direction, we see that we have force normal and force gravity. It's balanced, so force normal, remember it's the sum of, and force gravity is the opposing force. So I know that we've looked at gravity in the past in the downward direction as being positive. However, the force normal is working upwards, and upwards is our positive direction, and force gravity is working downwards against the force of normal. So it is an opposing force working in the opposite direction. A toy car rolling north across a carpet after a child has pushed it. So the direction of motion, we're going to call that way north now because we're the ones that set it. Here's our carpet, and here, wait for it, is our toy car. Now, is this toy levitating? In other words, is it hovering above the ground? Or is it being pushed down through the floor? And the answer is no. So force normal and force gravity are equal. And that's why this toy car stays on the floor. The child has pushed it, so there is no longer a force applied. In this situation, the child is crawling across the floor, so it is exerting a force against the floor. In this case, the child has already pushed the toy car, and so then the only force that's actually working is the friction of the floor against the toy car. And so in our x direction, force net will be equal to the force of friction. But which way is the force of friction going? It's going left, and left, west, those are all negative directions. So we're going to call it the negative force of friction. And in the y direction, force net is equal to force normal because that's our positive force, and the negative force of gravity. In other words, gravity is the opposing force to force normal. Okay, let's look at examples. It is going to be key to always draw a picture so that you're aware of what's going on in these diagrams. It says Fred is pushing a piano along the floor to the right at a constant velocity with a force of 250 newtons. Calculate the force of friction acting on the piano. So there's some key terms in here that we need to pay attention to. This first one here, constant velocity, means that there is no unbalanced force being applied, so our force net is going to be equal to 0. In here, it's asking us to calculate the force of friction. So draw the picture. Here's our fancy piano with the center being identified. The piano is neither levitating nor going through the floor, so force normal and force gravity must be equal. And it's saying that he is pushing, so actively pushing the piano, and the floor is going to act against it with the friction. Now, because it's asking us to solve the force of friction, we only need to look at the horizontal direction. Okay, that's the one that's coming into play. So when we look in the horizontal direction, which is x, we know that force net is going to be equal to force applied. It's going to be the sum of all forces in the x direction. So force applied plus the opposing force of friction. Remember, the negative sign just means it's opposing. Okay? When we insert our information, so over here we have force net is equal to 0.0 newtons, and it says the Fred is pushing a piano with a force of 250 newtons. So it's important that you understand what force that 250 newtons goes to, which is force applied. So we have 0.0 newtons is equal to 250 newtons plus the negative force of friction. And this sentence is equal to saying force net is equal to force applied minus the force of friction. I'm looking for force of friction, so I might as well make that one the positive. I'm going to bring this over to this side to make it positive, and I'm going to bring force net over to this side so that I can isolate force of friction. So force of friction is going to be equal to force applied minus the force of net. So force friction is equal to 250 newtons minus 0 newtons. Force of friction is equal to 250 newtons. One of the things that we didn't do at the beginning is we did not identify our direction. It doesn't say east, west. Oh, it says to the right. So our direction of motion is to the right. We know that the force of friction is an opposing force to our direction of motion. And so the answer is the force of friction is 250 newtons to the left. Okay? So that direction came from the free body diagram. Okay, that's what FBD stands for, free body diagram. Let's look at another example. A 482 Newton applied force causes a car to accelerate to the right along a horizontal road. The net force acting on the car is 150 newtons to the right. What is the force due to friction? First things first, what does this picture look like? Here's a car, and it's causing it to accelerate. This means that there's an unbalanced force to the right, so it's going to go this way. And because it's accelerating, we can indicate that it's unbalanced because force applied has this really nice long vector, whereas force of friction has a much smaller vector. So we show through our picture the unbalanced force. Okay? It says, what is the force due to friction? Again, this is in the horizontal direction only. So when we're looking at that, in the x direction, the horizontal, force net is going to be equal to force applied plus, because it's the sum of all forces, the force of friction, and we put the negative sign because it's an opposing force. It says that the net force is 152 newtons to the right, and the force applied is 482 newtons to the right. So we have 152 newtons is equal to 482 newtons minus the force of friction, and I just went plus times negative and I got a negative. Again, I want this to be positive, so I'm going to move this over to this side by adding force of friction, and I'm going to move 152 newtons over to here by subtracting 152 newtons. And so I'm going to have force of friction is equal to 482 newtons minus 152 newtons, which leaves me with 330 newtons. So all forces are directional. They're all vectors. They're not scalar. So we have force of friction is 330 newtons. And we know that in our diagram, force of friction is going to the left. So that is our answer. You're going to pause it here and work on these questions here at the bottom, page 78, 1, 2, 4, B, C, E, F, G, 6, and 7. Okay, now that you've had some time to practice looking at those particular forces, we're going to look at some other forces. A 12 kilogram object is pushed with a horizontal force of 6 newtons east across a horizontal table. If the force of friction between the two surfaces is 2 newtons, what is the acceleration of the object? So now we're upping our level of skill here. Start with a diagram. Here's our object, and it's pushed with a horizontal force of 6 newtons east. So our direction of motion is this way. Across a horizontal table, if the force of friction between the two surfaces is 2 newtons, force of friction, what is the acceleration of the object? Mass is also given to us, and the force applied is given to us. So we are going to look at what is the acceleration? Well, we've learned that in order to find acceleration, it's equal to force net over mass. This is what we're looking for. This we have, but we need to figure out force net. We know that force net, because we're only working with horizontal forces, it's going to come from the x direction. So we're going to have force applied plus negative force of friction. So force net is going to be equal to 6.0 newtons plus negative 2.0 newtons because it's the force of friction, which is an opposing force. And so we would get force net being equal to 4.0 newtons. When we go back into our equation, we see that acceleration is equal to 4.0 newtons divided by 12.0 kilograms. So then acceleration is equal to 0.3 repeating, and the units for acceleration are meters per second squared. Acceleration is a vector quantity, and so our answer is going to be, when we go back, we see 2 sig digs, 2 sig digs, and 3 sig digs. So it's going to be 0.33 meters per second squared. We ended up with a positive value. It says that it's accelerating, so we're going to say it's heading east. Okay. Question number 4. A 20 kilogram object is pulled horizontally along a level floor with an applied force of 27.0 newtons north. If the object is accelerating at a rate of 8.80 meters per second squared, what is the force of friction? So we're going to start with a diagram. The object is being pulled, so force applied, along a level floor with an applied force of 27 north. And so we're going to make our direction of motion this way, because it doesn't make sense to pull it up because now it looks like we're dealing with the vertical. So we're going to just turn our axis so that north is to the right. If the object is accelerating, so there is an unbalanced force at a rate of 0.80 meters per second squared, what is the force of friction? Okay, so we know this formula, force net is equal to force applied plus the negative force of friction. That's how we're going to solve this question. What is the force of friction? We have force applied. This is what we're looking for. We also have mass. How do we solve force net? Force net is always equal to mass times acceleration. So we got 20.0 kilograms multiplied by 0.80 meters per second squared. We know that we are going to get 16 kilograms meters per second squared, otherwise known as a Newton. And then from there, we can go back into our original equation where force net is equal to force applied plus the negative force of friction. And we can go 16.0 newtons is equal to 27.0 newtons minus the force of friction. I want this to be positive, so I'm going to move this to this side of the equation by adding it, and I'm going to move this one to this side by subtracting it. The opposite math function. This is a positive number, so I'm going to add a negative number to it. So I am left with the force of friction is equal to 27.0 newtons minus 16.0 newtons. And so the force of friction is 11.0 newtons. And it is, we forgot to draw it in, but it is an opposing force to force applied. Remember, it's one of the pairs. Force normal, force gravity are a pair. Force applied, force of friction is the pair. So if the force applied was moving north, that means that the force of friction is moving south. Okay? Then we have one last question. A 64-kilogram baseball player is running to home plate. When the baseball player is only 2.35 meters from home plate, she slides to a stop at the home plate to make a safe play. This is probably something Avery would do. If 895 newtons of frictional force are acting on the baseball player as she slides to home plate, what was her initial speed when she started to slide? So first things first, let's draw a diagram. Here's the baseball player, Bob Ross style. Here's home plate. Okay, she's sliding into home plate, so this is our direction of motion. Now, there is nothing pushing this girl to run to home plate other than her desire to get a point. But the ground is working against the baseball player, so we have force of friction. In other words, there's no force applied. The runner is already in motion. Okay, and then we need to list all of our pieces of information. So mass is equal to 64.0 kilograms. Distance is equal to 2.35 meters. Slides to a stop, code word for VF, is equal to 0 meters per second. Frictional force is 895 newtons. What's the initial speed? Those are our pieces of information that we have. So when we look, we have D, VF, VI. What can we potentially find when we have D, VF, VI? Well, we could use this squared, this formula. Right? VF, VI, D. There's no time, so we don't want to look at any of those other equations. So this is the only one that works. However, while VF is given and VI is what we're looking for, we have the distance. We need to find the acceleration. And the acceleration can come from our force net. Force net is equal to mass times acceleration. We have mass. Acceleration is what we need to find for this part. So now we need to do a third calculation, and we need to figure out how to find force net. We are working strictly in the horizontal direction. So force net, we can see that there is no force applied, but there is an opposing force to the direction. Remember, direction of motion is going this way. Force of friction is opposite of it. So we have a negative force of friction, for which we've been given a value. So force net is going to be equal to negative 895 meters. Now that we have force net, we can go back up into this equation. So now we're moving back up the equation ladder. So we're going to go negative 895 newtons divided by 64.0 kilograms. And our acceleration is going to be equal to negative, because we have that negative symbol there, 13.984 and multiple decimals meters per second squared. Now that I have solved this step, now I can go back up into the very original equation. Vf squared is equal to Vi squared plus 2AD. We're looking for Vi squared. Vf squared minus 2AD all square rooted will give us Vi. So Vf squared is 0. It came to a stop. So 0 minus, and we have 2 times negative 13.984, and you will use all of your decimals. And the distance is 2.35 meters is equal to Vi. A negative times a negative, we know our answer will be positive. We take the square root of it. This, remember, square root is where you're going to make an error because you're going to forget to do that step. 8.10719 meters per second is what this person was sliding into home plate with. So when we go back to the original question, we see 3 sig digs, 3 sig digs, 3 sig digs. So our answer, 8.11 meters per second. Velocity is directional, but she asked for speed, so we are actually solved because speed is scalar. If we have no information about force of friction, so say we weren't given this and we were given a force applied, or if there's said to be a smooth surface, then our force of friction is 0. If there's a smooth surface, then there's no friction inhibiting that object from moving. So now you're going to try page 80, 8, 9, 10, 13, 14, and 15.